Imagine you're standing in the middle of your room. Take a moment to look around. Everything in the space has a position relative to you. You want to describe the exact position of your desk lamp, but you could just as easily be thinking about the window, the door, or any object in the room. You could say, it's about 2 meters to the right and 1 meter forward from me. Or maybe the window is 3 meters to your left and 2 meters behind. This description uses distance and direction, and it's precisely what vectors do in mathematics. They let us describe not just where things are, but how to get from one place to another. A vector is like an arrow. It starts at one point and points directly to another, showing both how far and which way. It has a length, called its magnitude, which tells you how far to move. The longer the arrow, the greater the distance. It also has a direction, which tells you which way to go. The arrow could point north, southeast, or anywhere in between. In our example, the vector pointing to your lamp has a magnitude of about 2.2 meters, the diagonal distance, and a direction that's roughly southeast. Every object in the room can be reached by its own unique vector. Vectors are powerful because they capture the essence of movement and position. They let us track not just where things are, but how they change over time. They give us a precise language to describe where things are and how they move in space. This is essential in fields from engineering to animation, robotics to physics. Whether we're talking about a lamp in a room or a planet orbiting a star, vectors provide the framework for understanding spatial relationships on every scale. Thinking with vectors allows us to move beyond static locations and consider dynamic changes. We can predict, plan, and understand movement in a way that's both visual and mathematical. Just as a map guides us through a city, vectors guide us through the mathematical landscape of space and motion. They are the invisible arrows that shape how we understand and navigate the world around us. Think about throwing a ball, or even kicking a soccer ball across a field. The path the ball takes through the air can be represented by a series of vectors, each one capturing a tiny piece of its journey. Each vector describes the ball's movement over a short interval of time, its direction and speed at that instant. The direction of each vector shows where the ball is heading, while its magnitude tells us how fast it's moving. By adding these individual movement vectors together, tip to tail, we can recreate the entire arc of the ball's flight. This ability to combine vectors is fundamental to understanding movement. Just like mixing primary colors can create any color imaginable, combining basic vectors can describe any movement or position in space. In fact, any point in space can be reached by adding together the right combination of unit vectors, tiny arrows pointing in the basic directions. These are like our fundamental building blocks. Think of them as arrows pointing 1 unit to the right, 1 unit up, and 1 unit forward. By stretching and combining these, we can pinpoint any location in 3 dimensions, whether in the real world or in a computer simulation. This idea of vectors as building blocks is crucial for understanding how computers represent and manipulate objects in 3-dimensional space. By breaking down complex movements into smaller vector components, computers can simulate realistic motion in video games, animated movies, and virtual environments, making the digital worlds we experience feel dynamic and alive. The set of all possible vectors forms what mathematicians call a vector space. Imagine every possible arrow you could draw from the origin, in every direction and of every length. Together, they make up this space. This is like a vast playground, where vectors can roam freely and interact with each other. Just as people can move anywhere within a park, vectors can point anywhere within their space. Within this space, vectors follow specific rules that ensure consistency and predictability. These rules are like the guidelines that keep a game fair and organized. One of the most important rules is that you can add any 2 vectors together, and the result will always be another vector within the same space. This is called closure under addition. This is like saying that no matter where you walk in your room, you'll always end up at another location within the room. The space is complete. There are no gaps or missing spots. Another key rule is that you can multiply a vector by a number, called a scalar, to change its magnitude without affecting its direction. This is known as scalar multiplication. This is like saying that you can walk twice as fast or half as fast in the same direction. The path stays the same, only the speed changes. These rules, along with a few others, like the existence of a zero vector and additive inverses, form the foundation of vector spaces. They provide a rigorous mathematical framework for describing and manipulating vectors in a consistent and reliable way, no matter the context. This consistency is what makes vector spaces so powerful for solving real-world problems in physics, engineering, computer science, and many other fields. Whether you're designing a robot, simulating movement, or analyzing data, vector spaces are the invisible playground where it all happens. Imagine shining a light on a complex object, like a sculpture. As the light moves, the shadows shift and change, revealing different outlines and shapes on the wall. The shadow the object casts on a flat surface is a two-dimensional representation of its three-dimensional shape. Each angle of light gives a new perspective, a new projection. This is a simplified but useful way to think about projections. By tracing these shadows, we capture essential features of the object, even if we lose some detail. In mathematics, projections allow us to take information from a higher dimensional space and represent it in a lower dimensional one. This is crucial for understanding and working with complex data. We can think of this as flattening or slicing the information to make it easier to work with. Just like slicing bread or scanning an object, each slice or scan gives us a manageable piece of the whole. While we lose some detail in the process, projections allow us to focus on specific aspects of the data that are relevant to the problem at hand. This makes complex problems more approachable. For example, imagine you're designing a robot arm that needs to grasp an object. The robot can use projections to simplify the task. By considering only the two-dimensional silhouette of the object from the robot's perspective, you can determine the optimal angle and position for the gripper, making the process more efficient. Projections are essential tools for simplifying complex problems in various fields, from engineering and robotics to art and science. They allow us to extract meaningful information from high-dimensional data and visualize it in a more intuitive way, making the invisible visible and the complex understandable.